Today we're going to prepare something interesting that a lot of viewers have asked for and which we're interested in experimenting with. The Urushibara nickel catalyst. This is a nickel metal catalyst which is used for reductions and hydrogenation reactions in organic chemistry. Ideally you start off with nickel 2 chloride crystals, but we don't have those available. Instead we do have basic nickel 2 carbonate, which is a fine green powder as you can see here. We're going to start with 5 grams of this, and you can see the formula and the calculation of the moles of nickel metal on the screen. What might be useful to remember later is that this contains just over 2.3 grams of nickel metal. We've got a small beaker for this first part of the reaction. Let's get the basic nickel 2 carbonate in here. Be a little bit careful with this because nickel compounds are toxic and known to be carcinogenic. Fine dust like this is not something you want to be breathing in. First we're going to dissolve the nickel carbonate in concentrated hydrochloric acid. In theory this requires only a couple of mLs, but in practice it takes a bit more because the heat causes some to escape. We're starting with 5 mLs. We'll also add a magnetic stir bar. And now the acid slowly. It reacts quite vigorously. Soon you can see a deep green nickel chloride solution starting to form. So start up the magnetic stirring. And now carefully add more acid dropwise to the beaker. And keep going until you've got a nice clear green solution with all the solid dissolved. Nearly there now. The total volume of your final mixture should be about 10 mL. Okay, now for our next key ingredient. You can make Urushibara nickel with aluminium powder, but we're going to use zinc metal powder because it's available much finer than aluminium. We've got 10 grams here, which is a huge excess to what we need theoretically, but we'll explain why later. Place the fine zinc powder into a large beaker. Make sure it's got at least 200 mL capacity. And spread the zinc powder out across the bottom of it like this. You want the maximum surface area exposed. Okay, here's our nickel chloride solution. When we add this, a displacement reaction will occur with the zinc reducing the nickel chloride to nickel metal. And a lot of heat is going to be generated, plus some hydrogen gas. Let's rock and roll. According to the reports we read, the more violent this first reaction, the better the catalyst is that you end up with. So don't gently stir in the zinc powder like some and be delicate organic chemist. This is inorganic chemistry, so chuck it all in. After about 5 minutes the reaction has died right down and you can see that all of the green color has disappeared. So set up to filter this mixture. At this point we'd like to introduce you to a new lab addition. Yes, we've got a new glass sinter. A small grade 2-1. Santa was generous with us this year. We must have been very good boys and girls. Look at that subtle off-white coloring. The tasteful thickness of it. Oh my god, it even says Pyrex. Wash the beaker and the solid with about 50 mL of distilled or deionized water. Here we go. It's not perfectly dry, but looks like a dry powder. This is our intermediate product. What has happened is that some of the zinc particles have been partially covered in nickel metal, formed by the displacement reaction. The large excess of zinc we used ensures that the coating is partial and that there's still a lot of zinc remaining. Now what you do with this depends on the type of catalyst you want to make. There are two types, A and B. Type A is made by digesting this intermediate product with acetic acid, and is good for nitrile reduction reactions. Type B is made by digesting with an alkali hydroxide solution, and is good for ketone, oxime and other reduction reactions. We're going to be making type A today. So first we prepare our acidic digesting solution. Here we've got 15 ml of glacial acetic acid. You can also use propionic acid for this, but don't be tempted to use a strong mineral acid such as hydrochloric acid, as this is too strong. The effect it has on the surface of the nickel seems to render the catalyst inactive. Okay, let's get this into a 200 ml beaker. Now here's 80 ml of water, which together with the acetic acid will create about a 15% by volume solution. And now we add our intermediate nickel-coated zinc metal product. What's now happening is that the excess zinc is reacting with the acetic acid and dissolving, forming hydrogen gas. The reaction is fast to begin with but soon dies down. The color of metal becomes very dark, and after a few minutes you can see clumps of the solid floating on the surface. Give the mixture a swirl occasionally and leave it for a good 30 minutes to react. Once all the zinc dissolves, a very small amount of the nickel will also start to dissolve, and this forms a very faint green color in the mixture. Here we go. Held up to the light you can see it more clearly. Time to filter the product. Wash thoroughly with 50 ml of distilled or deionized water, and then with 2 portions of 10 ml each of absolute ethanol. This will get the product totally dry. And here we go. 4.1 grams of fine fluffy and almost black colored Urushibara type A nickel. There's about 1.7 grams of zinc still remaining in here, but that's apparently normal. Notice how dark colored and light and fluffy the powder is. This is what you want to end up with. Some people say that drying the product as we have done reduces its activity, but others disagree. So we're going to throw caution to the wind and try this out as it is. Okay, before we finish we'll do it again, but we'll show you what happens when it goes wrong. We start off again with 5 grams of the basic nickel carbonate tetrahydrate and make it up into a nickel chloride solution exactly as we did before using concentrated hydrochloric acid. The final volume of the solution is just under 10 ml. Now the difference. This time we're not going to use an excess of zinc. Instead we're going to use an excess of nickel salt, so here we're starting with 0.5 grams of zinc metal. This is a 2/3 molar ratio of zinc to nickel. We add this to our large beaker. Spread it out to increase the exposed surface area. And now we'll add the nickel chloride solution. Not very spectacular compared to last time. but lots of black colored metallic nickel in there. We filter this and wash as before with 50 ml of deionized water. The deionized water is important because some metal ions can poison the catalyst and make it inactive. Here's our intermediate. A lot smaller volume and a lot darker color than in the previous preparation. Okay, now for the digesting solution. We'll use 10 ml of glacial acetic acid and 50 ml of water to make up about a 17% solution by volume. And we'll put our intermediate in. This time there's a lot less effervescence. Any zinc metal remaining is encapsulated within the completely nickel-coated particles. We leave this for about 20 minutes and also warm the mixture gently to see if we can get a better reaction. After 20 minutes there's a faint green color, but this time a lot less material which is floating on the surface. So we filter and wash again as before. And with absolute ethanol to dry. Okay, here's the product. Hopefully you can see it's slightly different. It's denser in texture, more granular, not as fluffy looking, and isn't black like in the first preparation. Instead it's a dark gray color. The key to this catalyst seems to be in the acid digestion process with the zinc. If there's not enough zinc exposed to the acid, which can be etched away leaving the underlying nickel metal surface exposed, then the catalyst doesn't work. Too much nickel and there's no zinc to be etched away to leave this special reactive nickel surface. We'll be coming back to our catalyst to try it out in a future video. For now we hope you enjoyed the video, and stay tuned for more reactions.